All right, combinatorics. Okay, so this is no joke, this lecture that I'm about to give is probably one of the longest preparation times I've ever had. There are some things that we're going to talk about that are incredibly elegant and nuanced and actually don't end up being that complicated. But I really want you to grasp how beautiful what we're going to be talking about actually this stuff is. Okay, so I want you to go through this lecture carefully, try to understand everything that we're talking about. Believe me, it will be worth it. It's not difficult. If you have questions, make sure you come ask in some venue where that can take place. But this is really one of the most elegant, beautiful results in all of combinatorics. We're going to look at something called Burnside's lemma, which will eventually give us a way of counting the number of distinguishable colorings under some kind of group of symmetries. Okay, so please make sure you understand this lecture. Make sure you go back and review things from previous ones if necessary to clarify matters and whatnot. But I really had to think through how to do this justice in this venue. I think I might have a way, but we'll see if I can pull this off here. Just to let you know, the next homework set isn't due till Friday. I backed that off a little bit. It's just another set from 8.2. The next one after this will involve material from chapter 9 for the first time. So just be looking on the lookout for that. Everything's basically been backed off by at least a week at this point. Okay. Aaron Wentling asked me to hyperlink this document, this combinatorics notes document. So I have actually done that. That way you can easily, once, in the PDF form, click on chapter and section headings and go there quickly, as opposed to having to scroll through the entire document. So those sections and chapters have all been hyperlinked for your convenience in these combinatorics notes. I also made some editorial changes, some typos that I had noticed. So hopefully that will maximize the convenience of the notes document I've uploaded to Canvas. Let's talk a little bit about groups again. Okay, I wanted to revisit this definition down here. Now, I made a big deal of the fact that these permutations, the permutations that happen to be on the square itself, are just permutations of the four corners of the square. So the permutations are permutations of four elements, and they induce a permutation on the colorings themselves, and there were 16 colorings. So technically speaking, pi k and pi k twiddle aren't the same thing. Pi k twiddle arises from pi k. So please just keep that distinction in mind. I wanted to make that a key point up front just so that you don't confuse those two notions in your mind. But I will say that eventually I will drop the twiddle just because it starts to get cumbersome to have to write that down every time. So just be fairly warned about that. Now, the reason I write pi k twiddle is so that twiddle will remind you that this is a way that we get an equivalence relation on colors. We consider two colors to be equivalent. That's what this first line is right here. These two colors to be equivalent if there is a permutation, pi k, that induces a permutation on the colorings, pi k twiddle, such that pi k twiddle applied to Ci gives you Cj. So it operates on Ci and moves it to Cj. Okay. So and remember, we'd have to do this weird operation on the colorings on the left because of the way the book likes to read the permutations from left to right. It wants to think of them operating from left to right. So typically we would think of these permutations as a composition of functions. And when we compose functions, we always apply the rightmost function first because that's the inside function. Okay? So that's why I'm doing this weird thing of applying the coloring on the left so that it's consistent with what the book does. That way the book information will make sense as you're reading through it. Okay, so G is a set of symmetries, and we kind of defined what it meant for G to be a group. Okay, first of all, if I compose two of these permutations, all right, then I'd better land back into the group itself. Okay, I better end up with a symmetry that I'm accounting for. I better not get something new. Okay, so that's something that's fairly basic that we would require. That's called closure. Okay, we also, I didn't list it here, but we also need we also need these things to be associative, which means if I have three of them that I'm applying, that it doesn't matter whether I do the first two first or the second two first before applying the third. Okay, so associativity is a necessary thing as well, but that just follows from the fact that associativity under composition it holds. Okay, there's an identity element in there which basically fixes all the colorings. Okay, so or it induces a coloring that fixes all the colorings, and we made this little argument that showed that pi e twiddle, if pi e fixes the if pi e fixes all the vertices of the square or whatever shape you're looking at, then the color or the permutation that arises from that on colorings will also fix everything. Okay, and we made a little argument down here, right here, that kind of illustrates that. Okay, and then we said that if you have a permutation in here, then you also want to have its inverse. Okay, and the inverse is the thing that kind of takes you right back to where you started. So composing pi I with its inverse basically is like applying the identity permutation. Okay. Now I do want to say something about this. Last time as I was kind of reading through here, I was noticing some typos, and that kind of confused me a little bit. So I do want to say that this twiddle is an equivalence relation, okay, because of what we required up here. So for instance, axiom 2 gives us the reflexivity of the twiddle thing. So remember, we say that two colorings are equivalent if there is a permutation that moves me from the one to the other, right? The permutation induced by the vertex permutation induces a coloring permutation that moves us from the one to the other. That's what the equivalence relation is, okay? So how do I get reflexivity? Well, I have the identity thing. I have the identity, the identity symmetry, okay? And that thing fixes all the color, that fixes the coloring CI, right? So every coloring is equivalent to itself, okay? What about symmetry? If CI is equivalent to CJ, well, that means that there's a permutation that moves me from CI to CJ. Then is CJ equivalent to CI? Well, yeah, because I can apply pi k inverse to CJ, and that will send me back to CI. And of course, if pi k moves me from CI to CJ, then pi k inverse is going to send me back, okay? Right, so symmetry comes from the existence of inverses, right? So that's axiom 3. And then axiom 1 gives transitivity, okay? Axiom 1 gives transitivity. So if pi k applied to CI gives CJ, and pi L applied to CJ gives CM, then what about pi k pi L? That should send me from CI to CM in theory, and it does, because pi k applied to CI gives me CJ, and pi L twiddle applied to, right, these first two things would send me to CJ, and so that would send me to CM. Therefore, CI is equivalent to CM, right? So CI equivalent to CJ, and CJ equivalent to CM, which is encapsulated by these things, implies that CI is equivalent to CM. Therefore, all of these group axioms up here, these group axioms actually turn this coloring relation into an equivalence relation. Okay, so we need all of these: closure, identity, existence of inverses, and really we need associativity as well, associativity. I had 3 things I was applying. Okay, so that's where we were. So of course, if we have an equivalence relation, we know we get equivalence classes naturally from an equivalence relation. So if I take all the colorings of this object, all right, so like the square vertices of the square or something, then I basically get equivalence classes by letting the group kind of operate on these things, and that's just a consequence of this thing being an equivalence relation. The equivalence relation always divides up the set into equivalence classes, okay? So everything that happens to be an equivalence class is there because there is a permutation that moves me from the one coloring to the other, okay? So that's what it means to be in the equivalence class together. 2 colorings are only equivalent if there is some permutation that moves me from the one to the other. And so those belong to the same cell of the equivalence partition, okay? So last time we went through this, it just kind of talked about how if I have 2 separate elements in the group, then there's a unique permutation that moves me from the one, right? If I operate them together, then it's equivalent to the other one, to doing the other one. Okay, so that's a nice thing to have in our back pocket. Now, here we go. Burnside's, sometimes it's called Burnside's lemma if you're doing abstract algebra. In this class, it's called Burnside's theorem. Okay. Now there's going to be some notation for us to keep in mind as we're working through this. So just bear with me here. This is the same notation almost that the book uses. Okay, so I'm just trying to be consistent. And again, just so you know, I'm going to start dropping that twiddle thing for the permutation induced on colorings from the permutation on vertices. I'm going to start dropping that, but I don't want you to lose track of what's happening. Okay, so T is going to be the colorings of corners or edges of some figure. So you know, above we colored all the vertices of the square with black or white. So their T would have consisted of 16 separate colorings. Okay. But not all of them are really different. That's the whole point of this exercise. And then G is some group of symmetries of the figure, some group of symmetries. Now what's interesting here is we don't necessarily have to take all symmetries. We can take any group of symmetries so long as they obey those things that we listed above. Namely, they have to be closed, the identity has to be there, inverses have to be there. Okay, so any collection of permutations that satisfy those 3, this theory we're about to develop is going to apply. We don't have to have them all. If we just have some group of symmetries that works, it would be fine. So for instance, we might restrict our attention to a group of rotations. That would be perfectly acceptable, perfectly acceptable. Okay. So N, right, this is the thing that we really want. N is the number of equivalence classes of T induced by the group. Okay, that's what we want. Okay, so capital N is going to represent the number of equivalence classes. Okay, so above, remember we had like 6. Okay, that's the thing that we want to determine. We want to develop a general theory that will give that to us. And incidentally, because we're going to, from time to time, want to make reference to equivalence classes of certain colorings, we use this notation. E sub C is by definition the equivalence class of T containing C. Okay, so it's the equivalence class of T containing C. All right, so it's going to be, right, so E sub C is going to consist of all the things that C are equivalent to, which means there's a permutation that moves me from C to any other coloring that happens to be in that equivalence class. So T is like divided up perfectly into these like cells of the partition. Each one is an equivalence class of colorings. Okay, so like in our example, you had the all white one was its own equivalence class. You had a couple that were of size 4, you had one that was of size 2, and then, right, so I think there was 3 that were of size 4, there was 1 of size 2, and there were 2 of size 1. Okay, so those were all the equivalence classes of this, and we'll be looking at that example in a lot of detail eventually, okay? So here's the thing. So, if every element of the group, now remember, this is just a group of symmetries on our figure. If every element of the group takes a coloring to a different coloring, okay? So every single permutation in the group takes a coloring to a different coloring, then do you see that the size of the equivalence class is going to just be the size of the group, okay? Because every single permutation that I applied to C took me to a new element, okay? And that has to be all I could possibly do. I mean, the equivalence class, the equivalence class of C can't be any bigger than the group itself, because once I apply all the permutations to one coloring and I get everywhere that I possibly can, I'm not going to get new places by going to other colorings, because if that were possible, then I would have been able to like compose those permutations to get a new permutation that would have moved me from C to that thing, right? So I really can just kind of hone in on one coloring, look at where all the elements of the group actually send me, look at where all the elements of the group actually send me, and that's going to be everything in the equivalence class, okay? Look, by definition, it's in the equivalence class if there is a permutation that moves me from that coloring to any other coloring in that equivalence class. That's what the definition of that equivalence class is. So once again, I start with any coloring in the equivalence class and apply every element of the group, then that's going to actually exhaust all of the equivalence class, okay? And so if every permutation in the group moved a coloring to a different coloring, then the size of the equivalence class is going to be all of the group, okay? That's kind of a nice observation. If that were true all of the time, that is, that every, that every coloring in equivalence class moved us to a different coloring, then the equivalence classes would all have size equal to the group, okay? Would all have size equal to the group. And so every single one of the equivalence classes would have size equal to the group. And so then I would just have to multiply the size of the group by the number of equivalence classes, and I would get the entire, the entire collection of colorings, okay? And so you can see right here, that's what I'm basically saying. Okay, if that were true, if each equivalence class was the size of G, then I would have this formula clearly, right? The number of colorings would just be the size of the equivalence class times, which are all equal to the size of G, times the number of equivalence classes. So size of T, which in our example was, 16, right? 2 times 2 times 2 times 2, okay? And that would be equal to the size of the group times the number of equivalence classes. And so you would be able to solve for the number of equivalence classes, okay? But unfortunately, the size of EC isn't always the size of the group. Some colorings don't get sent to different places, okay? In our example, that definitely wasn't true. Like a lot of the equivalence classes had different sizes. And the reason that was happening is some colorings didn't get moved anywhere by some of the permutations, okay? They would just stay at the same place, right? So like you wouldn't even be able to tell that anything changed with a particular coloring for some of the permutations when we applied them to certain colorings, okay? In that example that we did earlier, N was 6, right? The number of colorings was 16, and the number of symmetries was 8. And look, if you take T divided by G, the size of T divided by the size of G, you get 2, which is definitely not equal to 6, okay? And incidentally, there's an example in the book that has to do with, you know, basically a triangle, an equilateral triangle with black and white, coloring those, and only thinking about rotations of the triangle, not reflections. Only thinking about rotations of the triangle. And in that example, you don't even get an integer. You get the size of T. So rotations of the triangle, there are 3 of them. There's the identity, rotation by 120 degrees, rotation by 240 degrees. And then you're back to the identity. Okay, so the size of G there is 3. If you have an equilateral triangle and you're coloring each vertex with 2 possible colors, there's 2 times 2 times 2 or 8 total colorings. So look at that. If you take size of T over the size of G, you have 8/3, which isn't even an integer, okay? Clearly can't equal the number of equivalence classes because it's not even an integer, okay? In that example in the book, it turns out that the number of equivalence classes is actually 4. Okay, and that makes sense because if I'm only thinking about rotational equivalence for triangles, the all white vertex triangle is 1 equivalence class. The all black vertex equilateral triangle is another equivalence class. And the other 2 classes are the ones that have 1 white and 2 black, or 2 white and 1 black, okay? So there's 4 equivalence classes, right? You have an equivalence class of size 1, another equivalence class of size 1, and you have 2 equivalence classes of size 3, okay? So there's a total of 4 rotationally distinct 2 colorings of the equilateral triangle. That example is right there in section 9.2 in the book. Okay, they talk about it about gathering around a table, but it's just rotations of the equilateral triangle. Okay. So what can we do? What can we do? Because it seemed like that formula was about to work, and then it got kind of messed up. Okay. The equivalence classes are all different sizes. Okay, this is pretty loose language going on right here. This isn't exactly what I want to say. I don't know that it's appropriate to say the size of the equivalence class is the size of the group. What we want to do is we want to count how the group is acting on each one of the equivalence classes in a different way. We don't just want to look at the size of the equivalence class. We want to look at the action of the permutations on elements in the equivalence class and have that be more consistent, okay? A consistent number, okay? The problem is, and we'll kind of look at this in more detail, the problem is, look at, I mean, for instance, the all white square. Everything fixes the all white square, right? The all black square, everything fixes that. That's why you have an equivalence class of size 1 in that case. All 8 permutations in our group of symmetries fix the all white, and all 8 fix the all black one. What's going on with those equivalence classes that are of size 4? Well, what's happening is each of those 4 colorings in those little rotation classes, each one of those 4 colorings is fixed by 2 permutations. And 2 times 4 equals 8. Okay? And what about, there was one equivalence class that had only 2 colorings in it. That was the one that had blacks and whites on opposite, on diagonally opposite, right? So black, black on diagonal, and then white, white on the other diagonal. There's only 2 in there. And what is going on there? Well, each one of those is fixed by 4 permutations, fixed by 4 permutations. And guess what? 2 times 4 is 8. Okay, so what we're going to try to do is take each one of those equivalence classes and think carefully about the way the permutations act on those equivalence classes so as to expand the number of, or expand in some sense the size, in quotation mark, of those equivalence classes so that they all have a consistent size. That way, we're going to be able to divide through by the size of the group and simply get the number of equivalence classes. Okay? And what I want to do is, I actually want to go back to the example that is up here, or I want to go to our colorings actually, which is up here. Okay. Okay. So so here's this. Okay. So first of all, what I want to do is I want to write down what these permutations actually are. Okay. So I'm going to do that. I'm going to actually do that on the screen here. So pi1 is the identity. Okay, so pi1, so let me just write this down. So pi1 is just the identity. Okay, is the identity. Okay, what about pi2? Well, pi2 is equal to rotation by 180 degrees. So I'm going to kind of write what that is. That's just this. So rotation by 90 degrees. Okay, what's pi3? Well, that's rotation in the clockwise direction by 180 degrees. Okay. Okay, what about pi4? Well, that's rotation by 270 degrees. Rotation by 270 degrees. Okay. And then what about pi5? All right, so pi5 says that you're going to reflect in the vertical axis. You're reflecting in the vertical axis. So that's the thing that goes like this. Okay, pi6. Okay, pi6 is the one that does that reflects in the horizontal axis. Okay, so it goes like this. It flips things like that. Okay, what's pi7? Okay, pi7 reflects in the negative slope axis. Okay, so it reflects in the negative slope axis, so it's like this. Okay, and pi8, okay, that's going to be in the positive slope axis. Okay, so I'm reflecting this way. Okay, there we go. All right, so those are the things, and I just wanted to write those down for our benefit later on as we kind of work through these colorings. So here was our here were our various equivalence classes, right? So T would just be the set of these things. Okay, so I'm just going to write that up here just so that we have it in our cognition. So T is equal to the set C1 ... C16. Okay, so T is just the collection of all of these things. Okay, and we're letting these permutations act on these colorings. Okay, and one thing that I want to point out here is I want to think carefully about how all of these permutations are actually going to act on these colorings. Okay, so first of all, it's fairly clear that that all of the permutations fix this coloring, right? So pi1 through pi8 all fix the first coloring. Okay. What about C2? What about C2? What's going on with that? Well, C2 is interesting. Okay, so let me just kind of think about this. So C2, okay, that arrow means C2 is just getting mapped to itself. What permutations do that? Well, clearly pi1 does. Are there any others that do that? Okay, so pi1 flips that to itself. None of the other rotations do. Right, those are going to kind of turn that thing around. Reflecting across the horizontal or the vertical axis, that doesn't. So that changes things. Reflecting in the horizontal or the vertical axis, okay. And the only one I see that, okay, and incidentally, if you reflect in the positive slope axis, that's going to flip those black and white corners back and forth. The only other one that seems to fix this is pi 7. Okay, that's interesting. Okay, so watch this. So what about C3? Let's kind of think. Let's think carefully about C3. What happens with C3? What things fix that? Well, you know, pi 8 fixes it, and so does the identity, right? So pi 1 and pi 8 both fix this. Okay, pi 1 and pi 8 both fix this. What about C4? Okay, well, pi 1 obviously will fix it. Okay, is there anything else that fixes this? Well, it seems to me that pi 7 does, and nothing else does. Okay, so pi 7 fixes it just like it fixed C2. Okay, so what about C5? Okay, what about C5? Well, pi 1 obviously fixes it, but so does what? Pi 8. Pi 8 would also fix it. Okay. Okay, that's interesting. Okay, but I really want to concentrate on C2. What is something that actually takes us from C2 to C3, for instance? Can you think of something that takes us from C2 to C3? Well, pi 2 definitely does. Pi 2 definitely does. Okay, but also, not only does pi 2 do that, also I could kind of flip that thing in the vertical axis, right? I could flip that thing in the vertical axis, so pi 5 also does that. And like I said, by definition, C2 is going to be equivalent to every other coloring in here. So there has to be a permutation that moves me to every other coloring, okay? So far I've applied 4 of the permutations to C2. You see that? I've applied 4 permutations to C2. What about C2? There has to be something that sends me from C2 over to C4. Okay, so what does it? What sends me from C2 to C4? Well, 180-degree rotation would do it, so that's pi 3. But also, what else would send me that way? It looks to me like if I reflected in the positive slope axis, that would happen. So pi 3, if I reflect in the positive slope axis, I think that would do that, right? Positive slope axis, yes. So pi 8. Okay, so far I've applied pi 1, pi 2, pi 3, pi 5, pi 7, and pi 8. And I've gotten, you know, C2 going to itself, C3, C2 going to C3, and C2 going to C4. Now what about what would take me to C5? Something has to do it, right? Because these guys are equivalent to each other. They're in the same equivalence class, okay? Well, it stands to reason that it would be the 2 remaining permutations. So like pi 4, which is rotation by 270 degrees, that definitely works. Okay, does anything else work? Well, presumably pi 6 would, which is reflection in the horizontal axis. That indeed, that does work, pi 6. Okay, and now let's not miss the pattern that emerges here. And by the way, I used C2 as kind of like a baseline example. Of course, I went to C3, C4, and C5, and I looked at, you know, I looked at what things happen to fix those. But concentrating on C2 does the job here. Notice something. Notice that I had 2 things that fixed C2, but I also had 2 things that moved me from C2 to C3. I had 2 things that moved me from C2 to C4. And I had 2 things that moved me from C2 to C5. That is going to be a consistent pattern with each one of these equivalence classes. The number of things that fix a coloring is going to be the same as the number of things that move me from one coloring to another, okay? And that's just going to be true for any one of these colorings. And in fact, it's going to be the same. In each one of these equivalence classes, they're going to be fixed by the same number of permutations. And that number of things that fix these colorings is going to be the same as the number of things that move us from one coloring to another. Right? It's going to be the same as the number of things that move us from one coloring to another. Okay, so that's sort of an amazing little picture there to bear in mind for sure. Okay. All right, and you could say, okay, so what do you think would happen? And this is very important for us to really hone in on what's happening with these things. And by the way, notice that now I've kind of thrown the tilde thing out the window. Okay, we're thinking of permutations that are moving the colorings around, and we're just going with it. Okay, we know what we mean. Okay, but just know in your mind that this is a different permutation from the permutations that we're operating on the vertices themselves. Okay, so yeah, what do you think is going to happen with C2 and C11? Okay, that little equivalence class down there. Well, probably something similar. So let's see here. So what things? Let's just kind of think about this. What things fix C10, okay? And how many things do you think are going to fix C10? Well, probably if the pattern persists, look at the equivalence class that had the coloring C1. There were 8 total things. The entire group fixed that thing, yes? So the number of things in that equivalence class times the number of things that fixed it is equal to 8, the size of the group. It seems like something similar happens with that upper right equivalence class. The number of things that are in that upper right equivalence class, we just looked at C2 through C5, the number of things that fix C2 times the number of things in there is equal to the size of the group. Okay? And incidentally, you could also say the number of things that move me from C2 to C3, or from C2 to any other coloring in the equivalence class, which is 2, times the number of colorings in the equivalence class is equal to the size of the group. That's amazing. Think about that. And that's something that we're going to have to prove. If we can prove that, we're going to be in amazing shape here. Okay, so once again, the number of things that fix C1, which is 8, times the number of things in the equivalence class, which is 1, equals the size of the group. Okay. Go into the upper right equivalence class. The number of things that fix C2, which is 2, times the number of things in that equivalence class, which is 4, is equal to the size of the group. Or you could say it as the number of things that move me from C2 to any other coloring, I don't care, C4, is 2, times the number of things in the equivalence class, which is 4, equals 8. That is no accident, my friends. That is something that is going to be a consistent pattern, and we are going to prove it, and it is going to give us precisely what we need. We're going to expand using that information, we're going to be able to expand the sizes of all the equivalence classes in some natural way to the size of the group, and therefore we're going to be able to divide through by the size of the group and straight up get the number of equivalence classes from that. So let's look at this. What would you predict about C10, for instance? Well, C10 and C11 have 2 things in that equivalence class. So my prediction, if this pattern is going to persist, is that you are going to have 4 things fixing C10, because 4 times 2 is 8. And you're also going to have 4 things that move us from C10 to C11. Okay? So what are the 4 things that fix C10? Well, as usual, we have pi 1, that fixes everything. Okay? What else fixes this thing? Well, certainly not pi 2, but pi 3 does. Certainly not pi 4, right? Because pi 4 would rotate by 270 and put that white vertex below where it started. What about pi 5? Reflection across the vertical line. No, that's going to change things. What about reflection across the horizontal line? No. What about reflection in the negative slope and the positive slope axes? Both of those fix this thing. So pi 7 and pi 8 both fix this thing. Okay, and let's think about what things move us. What things move us from C10 to C11? Well, presumably it would be everything else. Rotation by 90 degrees does. Okay, what else? Probably rotation by 270 degrees. Yeah, that certainly does. Okay, what else? Well, presumably reflection across the vertical axis, which is pi 5. Okay, and reflection across the horizontal axis, which is pi 6. Okay, so there it is. Sure enough, the number of things that fix C10 is equal to the number of things that move me from the one coloring to the only other coloring that happens to be in this equivalence class here. Okay, so that is exceptionally important for us to bear in mind, and that is the goal of what we're going to prove. I didn't want to do a whole bunch of abstract nonsense, which is kind of the tact that the book takes, roughly speaking. They just dive right in and start proving stuff, and you're thinking, why are we proving all this stuff? So our goal is going to be to show that in any equivalence class, the number of permutations that fix one coloring is the same as the number of permutations that fix any other coloring, and it is also the same as the number of permutations that move us from one coloring to any other coloring in the equivalence class. Okay, so that's what we're gonna be working toward doing. Yes, one more thing that I want to say before exiting this screen is that, of course, in this example, remember T is the colorings, but of course G is just the permutations themselves, right? So pi 1, pi 2, ... pi 8. And of course, in this particular case, we see flat out that N, which is the number of equivalence classes, remember capital N is the number of equivalence classes, is equal to 6, okay? N is equal to 6. So just so you know, I mean, we're gonna be referencing these kinds of things over and over again in kind of a more abstract setting. But here we see very clearly that T is the colorings themselves, G is the group of symmetries that are acting on those colorings. Again, I wouldn't have to do all 8 of these. I could do, only the rotations, for instance. Those would still satisfy all the things that we need to be true about a group, namely closure, existence of an identity, and inverses existing, right? So all of those things would exist even if I was only looking at rotations, but here we're allowing for reflections as well. Okay, and capital N is always the number of equivalence classes. Okay, so back down here, remember I somewhat imprecisely had said that we want to make it so that the size of each equivalence class equals or somehow gives rise to something that's equal to the size of the group, so that each one of those expands out to the same size, a known size, namely the size of the group, so that when we divide by the size of the group, we're just going to get the number of equivalence classes. That's the goal. And we think that we've already discerned how to do that upstairs by looking at the number of things that fix a given permutation. And we see that that's also the number of things that move us from one coloring to another in equivalence class. Okay, so, and that indeed is going to be the case. So that's why we want to prove this proposition right here. Okay, so here it is. This proposition is going to be the first thing that we want to prove. So suppose that there exist exactly R permutations in G that fix a given coloring. Okay, so now we're kind of getting abstract. But just remember what we were doing up there. That's why I did that example first up there. Okay, so there are exactly R permutations that fix C. Then there are exactly R permutations in G that map C to C prime for any C prime that's in the equivalence class of C itself. Okay, so that's one thing that we noticed up there. It looked like the number of things that were fixing each one of the colorings was equal to the number of things that moved me from any given coloring to any other coloring in the equivalence class. In fact, that would see, really, I could sort of say that that's true about any coloring. Pick a coloring, pick another coloring, right, pick a coloring, and then pick any coloring in the equivalence class, even the same coloring. Then the number of things that move me from that coloring to the other one you chose has to be the same number every time. Okay, that's essentially what's being claimed here. So if there are exactly R permutations in G that fix C, then there are exactly R permutations in G that map C to C prime for any C prime equivalent to C. Okay, of course, that's obvious if C prime is the same thing as C, because the number of permutations would just be the number of those that happen to fix it. So really all we need to do is consider any other coloring in the equivalence class itself and argue that the number of things that fix C is the same as the number of things that move us from C to C prime, okay? All right, well, let's try to prove this thing. Okay, so here's like a full-fledged detailed proof of what we want to show here. Now remember, what I said was that we desire to show that if I have exactly R permutations fixing a given coloring, and you give me any other coloring, okay, I mean, it could even be the coloring itself, but obviously that's going to have R things mapping C to itself because there were R that fixed it in the first place. But this is only interesting if you give me any other coloring that happens to be equivalent to this one. So let's assume that there are R permutations fixing the coloring, okay? So here's a little picture that I drew up here. Okay, I used some purple ink up here, right? So notice right up here what we're doing. Okay, so up here, what are we doing? Well, we're just writing down, well, assume that we have those R permutations, okay? And that they all fix the coloring C. And EC, okay, EC is the equivalence class of that coloring C. And I'm taking any other coloring C prime, okay? And I'm saying how many things move me from C to C prime? And we're assuming, of course, that all of these permutations are different from one another, okay? So that's what that's saying right there. So I'm assuming I have exactly R things that fix the original coloring C, and I'm looking at something that C is equivalent to C prime, okay? So in other words, C is equivalent to C prime, right? That by definition means that there are things that move me from C to C prime, okay? Well, the first thing that we do is we show that we can build R permutations. We can build R permutations from these things that fix C and move us to C prime. So first of all, because of the fact that C is equivalent to C prime, this is true if and only if there exists pi in G such that what? If I apply pi to C, remember I have to do this weird thing where I apply it on the left. If I apply pi to C, I get C prime. That is the definition of being in the same equivalence class. Okay, so I'm assuming existence of some permutation that moves me from C to C prime. But how can I build R of them from these R that happen to fix C? Well, like this. I do it right over here. Okay, so here's 1, here's 2, dot, 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 here's R. I claim that there are R permutations over here that happen to do the job. And how do I get them? Well, I take pi 1, right? So I'm right here, okay? I take pi 1 and pi and I operate them left to right, okay? Pi 1 fixed C, correct? And I'm operating that with pi. I know that I'm in a group, so this thing is closed. So that is still going to be an element of the group, something I can still operate on these colorings with. Okay, and I apply C, on the left. So what does pi 1 do to C? Well, it fixes it. Okay, so it fixes it, and I just end up, right, so it fixes it, right, pi 1 is just pi E. And I end up just getting C, and of course pi applied to C is C prime by assumption. And I can do a similar thing for all of these, right? Pi 2 applied to C is just C because it fixes it. And I apply pi and that sends me to C prime. Okay, all of these are sending C to C prime. And could these, right, and my claim here is that all of these things are actually different, right? So how? How are they all different? Well, notice the following. If pi pi were equal to pi j pi, then all I would have to do is operate pi inverse on the left, right? So I could just operate pi inverse on the left, or on the right actually. If I operate pi inverse on the right, that would mean that pi I was equal to pi j, okay? So all of these have to be different, okay? So yeah, all of these have to be different from one another because the pi 1 through pi r are all different, okay? So if I ever had two of these guys that were the same, then, or if I ever had like pi 1 pi and pi 2 pi, if those were the same, then pi 1 and pi 2 would be the same, but that would contradict the fact that they were different in the first place. And in fact, maybe that's a better way to write this, just to make sure that we're on the same page here. So if, right, so let me just say if, for example, pi 1 pi were equal to pi 2 pi, then what you could do is you could operate on the right by pi inverse on both sides. Pi inverse would be the identity, and you would get that pi 1 was equal to pi 2. Contradiction. Okay, contradiction. Okay, because pi 1 isn't the same as pi 2. So all R of these are different, okay? All R of these are different things that move us, right? So here's pi R, dot, dot, dot. Here's pi 2 pi, and here's pi 1 pi. Of course, pi 1 pi is just pi itself, okay? Because pi 1 is the identity. Could there possibly be other things that moved us from C to C prime? Remember, what we're trying to show is that there's exactly the same number of things moving us from C to C prime as there are fixing C itself. If there are things fixing C, then there are things that move us from C to C prime, okay? So are there others? Are there others? Well, suppose that pi prime moved C to C prime, okay? So here I'm assuming that pi prime moves C to C prime. Well, what's true about pi inverse? Remember, pi, okay, so going down here, pi moves C to C prime. Well, if pi moves C to C prime, think about this for a second. That means that pi inverse applied to C prime is just, right, that just sends us back to C. Okay, so that's all I'm saying right here. Since pi inverse of C prime is C, what are we going to have if we apply pi prime, pi inverse to C? Okay, right here. What are we going to have? Well, pi prime of C is equal to C prime. Yes, that's what the assumption was. So that gives us C prime, but then pi inverse applied to C prime gives you C. So that means that pi prime, pi inverse fixed the coloring C. It didn't move it at all. So that means we know all the things that fix C. That's these guys up here, right? So that's these guys up here, pi 1, pi 2, dot, 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 all the way up through pi r, okay? So if pi prime, pi inverse fixes C, it has to be equal to some pi I for some I, okay? But then if I just multiply on the right by pi, right? If I operate on the right by pi, that means pi prime is equal to pi I times pi. Okay, and so it is among all of these things we just constructed. Okay, it's among all of those things. So there it is. So in other words, can there be others? So there are no others. Exclamation point. Okay, so R permutations fixing C implies that there are R permutations exactly R, right? So these are, right, so exactly R permutations fixing C implies that there are exactly R permutations mapping C to C prime, okay, which is equivalent to C, okay? That's interesting, okay? So again, if I have R things fixing a coloring, okay? If I have R things fixing a coloring, what have we shown? If I have R things fixing a coloring, then there is going to be R things exactly that are going to move me from that coloring to any other coloring in the equivalence class, okay? So that is a fascinating little tidbit to have in our back pocket. All right, so we've proved this. That is, if there are exactly R permutations in G that fix C, then there are R permutations in G that map C to C prime for any C prime equivalent to C in the same equivalence class. And we proved it. That's kind of a, you know, what I did over there, and when I was writing out the proof, is I was giving you a visualization of what's happening right here in the notes as kind of an analytical stab at how this works. It's still a proof though. Okay, and here's a little corollary. Okay, here's a corollary that I want us to concentrate on for sure. So this corollary right here. Okay, what does it mean? Okay, again, we know that if we have R things fixing a coloring, then there have to be R things moving us from that coloring to any other coloring that it's equivalent to. But now let's kind of start with C and C prime, okay? So whether it happen to be equivalent. Then the number of permutations in G that fix C is the same as the number of things that fix C prime, okay? So we know that if I have R things fixing C, then there are going to be R things that move me from C to C prime, okay? That's already true. But then I'm claiming further that there are also going to be R things that fix C prime itself, okay? So R things fixing C implies R things that move me from C to C prime. And I want to claim that there will also be R things that fix C prime, okay? So let's prove that. And then I think we're going to be in business big time. Right. Okay, so here's what we're going to do, and we're going to do to show this. Again, the idea is if we want to show that any coloring that's fixed by exactly R permutations is also moved to anything that it's equivalent to by exactly that same number of permutations. And then anything that it moves to in its equivalence class, that too is fixed by the same number of permutations. So this is, you know, what else could we ask for? This is like an amazing counting of things, right? If two things fix a coloring, then anything that's in its equivalence class, two things are going to move it from that coloring to that other coloring. And also two things will happen to fix that coloring over there. Okay, so we're just kind of tracing our way around inside of this equivalence class. Okay. So here's the proof of the fact that two equivalent colorings are going to be fixed by the same number of permutations. Well, I'm going to kind of take a strange approach here. What I'm going to do is I'm going to do like the reverse of what we did before. Before we started with R permutations that fix a coloring, and we showed that there has to be R things moving us from that coloring to any other coloring it's equivalent to. I'm going to go backwards. What if instead you started with R permutations that move us from C to C prime? So that is, suppose there are exactly R permutations that move from us from C to C prime in its, right, in C's equivalence class, right? So what if we instead start with exactly, okay, so this, right, I just want to make sure it's very clear. We're talking about exactly R permutations that move C to C prime. Okay, so name them sigma 1 through sigma R, and all of those move C to C prime. That's what this is saying right here. Okay. Okay, so of course the identity permutation always fixes the coloring C. So again, sigma 1 through sigma R are things that that fix or that move C to C prime. Okay, so I've just taken something that C is equivalent to. So we're just saying that C is equivalent to C prime. Okay, so C is equivalent to C prime. So in other words, you know, C and C prime both belong to, of course, C belongs to the equivalence class of C, but so does C prime. And incidentally, just like before, C equivalent to C prime means that there exists what? There exists a permutation moving us from C to C prime, but I actually have a whole bunch of those, right? There exists, right? I'm not even going to write this down because it's just obvious. Okay, I'm assuming that there are a whole bunch of permutations that move us from C to C prime, and that guarantees equivalence, right? So, so yeah, we have that right here. All R of these happen to do that, okay? But the identity clearly fixes C. I want to construct a bunch of things that happen to fix C here, and here's how we're going to do it. Okay, so what if I take sigma 1, sigma inverse? Okay, well, clearly that's just the identity, and that's going to fix C. So there's 1. Okay, what if I take sigma 2, sigma 1 inverse? Well, what does sigma 2 do to C? Well, all of these things send C to C prime. Okay, so here's the second thing right here. Sigma 2C is C prime. Okay, and then if I apply sigma 1 inverse to that, well, I know that sigma 1 sent C to C prime. So sigma 1 inverse sends C prime to C. Okay, so both of these first two things do that. And similarly, I just go on down the line and I have R things. So sigma 1 inverse, sigma 2 sigma 1 inverse, dot, 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 sigma R, sigma 1 inverse. All of these send C to itself. They all fix, right? So all of these fix C. All R of these fix C, okay, which is important, okay? And again, they are all distinct. They are all distinct because sigma 1 through sigma R, right? All of these guys were distinct, right? Up here, okay? Dot, 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 right? All of these guys were distinct. That's what we assumed at the beginning. So that means all of these are distinct because if any two were the same, we could just multiply through by sigma 1 on the right and just show that like sigma 1 and sigma 2 were the same, okay? So these are distinct permutations fixing C. Could there be others? Okay, well, by the same argument, if sigma was something that fixed C, okay, if sigma was something that fixed C, then of course, what would happen here? If I took sigma sigma 1 and applied that to C, okay, sigma C is just C, okay, but sigma 1C sends me to C prime. So in other words, sigma 1 sent C to C prime. So that has to be accounted for among these sigma 1 through sigma R. Those were the only things that sent C to C prime. So sigma 1 would have to be equal to sigma I for some I, okay? Okay, so what does that mean? Okay, well, if I multiply by sigma 1 inverse on the right, when I say multiply, I mean just apply it, okay, compose it on the right there, okay? Then you get sigma is equal to sigma 1, sigma I, sigma 1 inverse, which is exactly among all of these guys that happen to be up here, okay? It's among those. Okay, so that's all there are. So the R permutations mapping C in the equivalence class of C to C prime in the equivalence class, right? So exactly, let me re-emphasize the word exactly. Exactly, R permutations mapping C to C prime implies exactly R permutations fixing C. Okay, so whether you start with R things fixing the coloring, you'll be able to build exactly R things moving us from C to C prime, or if you start from R things mapping C to C prime, then you can construct R things that happen to fix C. And by the way, I could have gone backwards. If I have R things moving me from C to C prime, then I also have R things moving me from C prime to C, namely the inverses. You see what I'm saying? I'm using all of these axioms that we had at the beginning about the groups, namely that I have inverses. So if I have R things going from C to C prime, then I automatically have exactly R things going back from C prime to C. And therefore, what that means is, since I have exactly R things going from C to C prime, we just showed that there has to be R things fixing C. Then there are also exactly R things moving me from C prime to C, namely the inverses, yes, namely the inverses. And by the same rationale, I have exactly R things moving from C prime to C. That means I also have R things fixing C prime. So we have it. We have everything we said we could possibly want with these things. The number of things that fix C is the same as the number of things that move it to anything else in its equivalence class is the same as the number of things that fix, anything that you can move it to in its equivalence class. Okay, so all of those numbers are the same, which is exactly what we were seeing back there before. We had two things fixing those colorings and two things moving us to any one of the other colorings, and each one of those was fixed by two permutations. Okay, 2, 2, 2 all over the place in that equivalence class of size 4. All right, that is remarkable. Let's bring all of this home. I promised that something big was going to happen, and it's about to happen. Okay, so first of all, what I want to do is I want to say, well, okay, so T, remember T was the set of all colorings. So what I want to do is I want to write it as a union of the equivalence classes of colorings. So EC1 union, right? It's a disjoint union. That's what that little dot means right there, okay? Remember dot, you may or may not recall that that means disjoint union, okay? Disjoint union, okay? So EC1, union, EC2, union, and by the way, I'm just out of convenience choosing a representative coloring from each one of those. And since I want to be able to kind of count the number of equivalence classes, and remember we denoted that by capital N, I'm indexing the colorings in that way. So this is C sub N. Okay, so notice that there are N equivalence classes. okay? Or inequivalence classes here, okay? So, and this is the set of all colorings, okay? So, I mean, the picture that we have, generally speaking, okay, so if I let C just be one of these representative colorings from these equivalence classes. Now again, remember, so there's no way to move like C1 to C2, for instance, because those reside in different equivalence classes, okay? But C1 can be moved to anything inside of its equivalence class, okay? So I want to draw this like little generic picture here of what's happening, okay? So this is the equivalence class of C, okay? And okay, here's C itself. And I don't know, maybe C prime is somewhere in here. So here's this coloring C prime. Okay, I want to label the number of things that happen to fix this. Okay, so there's one, there's another one, dot, 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 there's another one. Okay, so there's a whole bunch of things that are going to fix this thing. Okay, so the number, so let me just say that the number that fix C, I want to give that a name. We were kind of calling that R before, but I'm going to call that phi of C. Okay, so that's the Greek letter phi. Okay, now we're not talking about the Euler phi function here, which came up in our last homework set. This is just phi of C. It's the number of permutations, by the way. It's the number of permutations that happen to fix this particular thing, if you will, okay? Then of course, you know flat out that the number of things, we already proved this, okay? So how many things move us from C to C prime? Okay, so that number of these is going to be equal to phi of C again, okay? Whatever the number is that fix C is equal to the number of things that happen to move us from C to C prime, okay? And by the way, that's also the number of things that happen to fix C prime also, okay? So the number of these is equal to phi of C, is equal to phi of C, which is phi of C prime also. Okay, all of these things are the same. Okay, and even if I went backwards from C prime, that number would be phi of C as well. Okay, so that's important information. Let's try to make use of that somehow. Okay, let's try to make use of that somehow. Let me ask you a question. So if I were to actually look at the sum, okay, so think about this. So note the following. This is kind of an important thing to note. What would happen if I were to take and actually add up all of the phi of C's for each one of the colorings in an equivalence class, okay? Well, all right. So let's see here. You know, if I go phi of C, okay, so that is, okay, what am I doing here? Suppose I take, let me erase this thing right here, okay? So let's just kind of talk about this for just a minute together. What is going to happen if I actually look at the number of things that, so if I actually look at the number of places that my coloring gets sent by all of the permutations in the group, okay? Well, I'm just going to get the size of the group itself, yes? I'm just going to get the size of the group itself, okay? So, in other words, what I'm saying is, okay, so suppose I take phi of C plus phi of C plus dot, 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 plus phi of C. And I do that a total of the size of E of C times, okay? What am I going to get? Well, I claim that that's going to be equal to the size of the group itself. How? Well, because when you think about, okay, applying all of the elements of the group to the coloring C, all the stuff that we did over there, the first phi of C is going to be basically the number of things that fix C itself. And then I look at stuff that move me to other colorings in the equivalence class. Okay? I look at other things that move me to other colorings in the equivalence class. By the way, there are a total of the size of E of C of those. That would include the coloring itself. How many permutations are going to move me from one coloring to another coloring? Well, it's always going to be phi of C, the number of things that fixed, right? Phi reminds you of fixed, by the way, just so, so it's well-chosen notation. Phi reminds you of fixed, right? It's the phonetic letter for F in the Greek alphabet, okay? But the number of things that move me from C to another element in the equivalence class is also phi of C. And that's going to keep happening, right? There are going to be phi of C things that move me from that coloring to any other coloring, okay? And that is going to happen for each one of the elements in the equivalence class. There's going to be phi of C permutations that move me from a coloring to any other coloring in the equivalence class. So when I add all of those phi of C's together, there are the size of E of C of them. I am going to get the size of the group. I'm going to get the size of the group, which is amazing. Okay, another way to write this is this way. Okay, so let me just say the sum over, C in E of C. Okay, well, maybe I better use C prime in E of C. Phi of C prime, which, by the way, is the same as phi of C. Okay, so this is just the sum over any coloring that happens to be, so C prime and E of C, phi of C, right? Because phi of C is going to be the same as phi of C prime because they're in the same equivalence class. This is going to be the size of the group, okay? The size of the group. All right, well, why does that matter, or why is that helpful at all? Well, because of this, right? So watch this. Watch what happens. This is the amazing punchline of all of this. What happens if I take and I sum over all colorings, okay, phi of C? What happens if I sum all of those together? Well, we know that T, right, what did we do up here? We wrote T as a disjoint union of all this junk. Remember that? Okay, so really I can just go through each one of those equivalence classes of colorings. Okay, so let's go ahead and do that. Okay, so what happens? This is the same as the sum I going from 1 to capital N. Okay, the sum of C belonging to the equivalence class CI. Okay, because again, T was a disjoint union of those things. Okay, and then I just go phi of C. Okay, right? We know, right? Look at that's because of this identity up here. We know that if I add up these things, I actually know what each one of these is. Okay, so this guy right here, if I add up all of the phi of c's over an equivalence class, I am just going to get the size of the group every time. So this ends up equaling, this is the amazing part, this ends up equaling the sum, I going from 1 to n, the size of the group. But that's just a constant. So look what we get. This is just going to be n times the size of g. Right? N times the size of g. Thus what? N, the thing that we wanted, like the number of equivalence classes, right? The n was the number of equivalence classes, is equal to 1 over the size of the group times the sum, times what? Times the sum over colorings over all possible colorings, phi of c, okay? Look at that amazing formula right there. Okay, that's actually what Burnside's theorem says. It says that n is equal to 1 over the size of the group times the sum over all possible colorings, phi of c. Remember what phi of c equals. Okay, let me just kind of write it down over here so that it's on the board. But phi of c is equal to the number of pi belonging to g that fix c. Okay, so it's the number of permutations that fix the coloring c. Okay, that is remarkable. Okay, now this formula right here is actually not the most convenient to work with. So I'm going to do one last tweak on this and then we'll be done. We'll apply it in the case we've been working on. But this right here is the essence of Burnside's theorem, okay? Burnside's theorem, okay? Okay, one last tweak to this thing and we'll be done. Okay, so what we have shown so far, okay, what we've shown so far is that right, so I've kind of rehashed everything here so that you just have it all here in one place. T is the colorings themselves, G is the group of symmetries on those colorings, N is the number of equivalence classes when G acts on those colorings, and phi of C is the number of permutations that actually fix the coloring C. Okay, so phi fix C, right? It's a number of permutations that fix that particular thing. So what we've shown is that this is the formula for the number of equivalence classes, right? So that's what we wanted to get. But there's one last tweak that we want to do here, just to kind of show this in all of its glory. So here's something to note. Okay, so note the following. If I add up over all colorings, okay, so phi of C. Look, I can kind of write this in a funny way. Okay, let me write this way. It's the sum over C and T, the sum over pi belonging to the group. And what I can do is I can basically just say, look, just B1 if pi of C happens to be equal to C. Okay, what does that mean? So where, let me just say, where one of this, what is this? It equals, is equal to 1 if pi of C equals C and equals 0 otherwise. So it's only equal to 1 if pi happens to fix C, okay? And so it's exactly going to count those things which fix C in that innermost sum. And therefore, this thing right here is just, I mean, for crying out loud, that's just a funny way of writing phi of C, okay? Well, one of the greatest tricks in all of mathematics when you have a double sum like that is to actually flip the order of summation. So let me write this as the sum pi and g, the sum c and t, the indicator, right? This is called an indicator variable. Let me just write that in here, right? So this is an indicator. It indicates if whatever I put at the bottom is true. So this is the indicator function. Okay, it's an indicator function. Okay, indicator function. Okay, so back over here, let me go back to black here. So this is 1 of pi c equal to c. So it's the indicator of whether pi happens to fix c. Now look at this innermost sum right here. What is this? What's this innermost sum? Okay. Now I'm running over all of the colorings. Pi is fixed, right? Right? So it's the number of colorings. It's the number of colorings, C, that pi fixes, okay? Okay, so again, pi is like the fixed thing here. So it's the number of colorings. That's slightly different than the other one, okay? So look, we're gonna give this a name. We're gonna call this psi of pi, okay? So it's psi of pi. It's the number of colorings that pi fixes, right? So it's just the number of colorings that pi happens to fix. Okay, so when we do that, look what we get. This just ends up being equal to the sum over pi belonging to the group psi of pi, right? So this right here is the Greek letter, right? This right here is the Greek letter psi. Okay, right, just so that you know. So it's the number of colorings that pi happens to fix. So that's another way to write this. Okay, so that sum over colorings, phi of c, is equal to the sum over permutations, psi of pi. So I can either think about summing over colorings or summing over permutations themselves. Okay, so that is a big deal. Okay, that is a big deal. And we're going to use that to kind of finally state Burnside's theorem and use it to solve our original problem. And then on Thursday, we'll come back to a whole bunch of examples. And so here we are. This is Burnside's theorem. This thing was proved in 1897. Okay, so this thing was proved in 1897. Right, so it's a fairly old result. Okay, and here it is right here in all of its glory. Okay, we've proved it completely. Okay, so the number of equivalence classes, gotten at by letting G act on the colorings is equal to 1 over the size of the group times the sum over colorings phi of c, where phi of c is just the number of permutations that leave c fixed. Or you can write it in another way, which I just showed you. N is going to be the 1 over the size of the group times the sum over permutations in the group, psi of pi, where psi of pi is simply the number of colorings in T that fix pi. It's the number of or the number of colorings in T that are fixed by pi. And generally that second one is slightly easier to deal with. Okay, slightly easier to deal with. So let's see this finally applied in our example here, okay? So here's our square problem right here. Okay, so let's see it. So in the first formula, remember what we had, okay, 1 over 8. So N is the number of equivalence classes. Okay? N is the number of equivalence classes. And that's what we want. You go 1 over the size of the group based on Burnside's theorem. okay, 1 over the size of the group. And then you go over all the colorings. Remember C1 is the all white vertex coloring. How many things fix that? Okay, so this guy right here corresponds to C1, if you think about it for a second. Okay, or this right here is actually phi of C1. Okay, and this 2 right here, that's coming from phi of C2. Okay, and in here, what I was actually doing was I was writing down what the two permutations were giving rise to that 2, right? So the number of things that fix C2, there are 2 of them. Similarly, there are 2 things that fix 2 permutations that fix C3. There are 2 permutations that fix C4, 2 permutations that fix C5, 2, 2, 2, right? It goes on for a while. And then we got to C10 and C11. Both of those are 4s, okay? And then we had 2, 2, 2, 2 again, okay? There was C15 right there. And of course, the last one was the all black thing. And how many things fix that? How many permutations will all 8 fix those ones? Okay, so amazingly, what do we end up with here? Well, I have a couple of 8s. How many 2s do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 2s. And how many 4s? 2 of them. Okay, so 2 times 8 is 16, plus 24, plus 8. Okay, so that's 48 over 8, which is 6. Amazing. That's exactly what we were hoping to get. Think about it for a minute. Okay, so what about the second formula? Okay, what about the second formula? Remember, that was the one that involved psi of a given permutation. Okay, so what I do is I'm going to go through here and actually look at each one of the permutations. So right, we want to count the number of colorings fixed by those permutations. And I am telling you, so where is this 16 coming from? Well, that 16 is coming from psi of pi 1. How many colorings are fixed by the identity? All of them. So that's 16. Where is this 2 coming from? Well, that 2 is coming from, so I look at pi 2, which is 90-degree rotation. 90-degree rotation. How many colorings are fixed by 90-degree rotation? Well, the all white one and the all black one. That's it, right? So this is psi of pi 2, if you think about it for a second, okay? 4 is psi of pi 3. 2 is psi of pi 4. You can kind of think about all these. You just count the number of colorings that are fixed by these things, so on and so forth. So I have a 16. I have 2 2s. I have 3 4s, and I have 2 8s. Okay, so that's 16 plus 4 plus 12 plus 16. Okay, so that's 20 plus 28, which is 48. And lo and behold, we get 6. Okay, and as we said, the numbers in the second formula come from counting how many times a given permutation occurs in the first formula. That's kind of what I was doing when I was switching the order of the double sum. But you can go back and watch that. I promise that works out nicely. If it's really sort of intuitive if you do that indicator function approach I did back there. So wow, hopefully that's kind of a satisfying end to this whole exploration. Burnside's theorem is a very, very big deal. And really it was the key that Polya needed to solve his problem on isomers, okay? So there's going to be a lot more interesting combinatorics coming from here. Now that we have Burnside's theorem, it's going to start becoming more and more important that we find clever ways of counting these either phi of c's or psi of pi's, Those things are going to be the things we're interested in counting now, since they're the things that appear in Burnside's theorem formula. Okay, so that's what the rest of chapter 9 is going to be devoted to. All right, that, my friends, is all for now.